We are continuing on the topic of controllers, then FSMs, finite state machines, implementation of state machines, Mealy and Moore machines, and then starting with state diagram, going through the Carnot maps, and eventually coming up with the circuit. And then also we talked about Verilog descriptions. I'm going to be talking about a different kind of implementation today, and that is what is referred to as one-hot implementation. Okay, it is again the same circuit, the same description, and then you come up with the circuit realization of it. Except that you don't go through the state machines. You don't go through the transition tables, excitation tables, flip-flops, this, and that. And then you do what is referred to as one-hot implementation. So let's talk about one-hot implementation. What I'm showing you here is our own Mealy machine, which we did 1, 2, 3, 4 states, and then remember we did 2 flip-flops and realized it completely, and Verilog and all that. Let's not get into that. I'm only talking about a certain realization now. So what I'm going to do is the following. I will realize this circuit, not going to the state tables and following the path we talked about. Remember, the state table, transition table, excitation table, Carnot maps, combinational realization, putting flip-flops in and then feeding back, and that's it. Okay, and then you came up with the circuit. Here, I'm going to skip all of those. I'm going to say, why don't I give state A 1 flip-flop and 1 to B, 1 to C, 1 to D. The flip-flops I have are asynchronous reset and rising edge clock. That doesn't really matter what kind of flip-flop I want to be using. Okay? So that's this, that's this, that's this. These are the clock inputs. Let me use a different color for the reset inputs. Okay. And then we have the 4 flip-flops that are A, B, C, and D. And when I am in state A, that means this output is 1, this, or this. Okay? And now I'm describing each flip-flop, okay, or each state. When I'm in state A, I either go back to state A or I go to B depending on the value of J. What it means is, depending on J, if J is 0, see, when I am in state A, I'm saying something, turning it into gates. When I am in state A, that means when this signal is 1. If J is 0, then I activate state A. See, when J is 0, I activate state A. And when J is 1, I activate state B. Again, when I'm in A, if J is 1, see, I'm not using a bubble for the right-hand side, and it goes into state B. But then I look at the state A, I see that there are several possibilities that I go to state A, and therefore if I just put this into state A, then somebody else wants to come into state A, and then I have problems. So what I do, I will think ahead and say, well, why not I put an OR gate here? So for now, I take this output into state A, but then later on, I will put another output from another place, which you can see state C also comes back to A. I put that into A as well. All right, how about B? B the same way. So what I'm really doing is I'm putting OR gates next to each of the inputs of the flip-flops. Okay, let me mark the flip-flops and everything. Now let's put two AND gates back to back on every one of my outputs. On every one of the outputs of the flip-flops back to back. 1 for 0, 1 for 1. 1 for J0, 1 for J1. Okay. I haven't done the output. I will do the output. All right, let's go to state B. State B, I'm going to be using this color. A 1 takes me back to state B. A 1 takes me back to state B. A 0 takes me to state C. A 0 takes me to state C. Okay, let's do state C. State C is this one. A 1 takes me to state D. A 1, that means the AND gate on the right hand side, takes me to state D. A 0 takes me to state A. Okay, a 0 takes me to state A. The good thing is we have enough colors. Then we have, let's do this. Okay, state D. A 1 takes me to, a 1 takes me to B. A 1 takes me to B. I have to find a nice way into B. I go from the bottom. Okay, a 1 takes me to state B. And a 0 takes me to state C. Okay. Put back the red one. Okay. The OR gate on D, I don't really need that. But that's okay. To be consistent, it's good to have a slice and keep repeating it. Now, let's look at the output. The output says when you are in D and input is 1, the output is 1. Okay? So when I'm in D, which is this line here, and input is 1, means ANDing. The output is 1. Actually, this is no different than this line over here, but in order to just make it separate and make it because usually it doesn't happen that easily that the same gate that you already have, it's also providing the output. Maybe there is a place where your output is, you have two outputs and in two different places, and therefore you have to bring those and AND them, OR them, and so on. And also this is mealy, and therefore you are seeing that the input is contributing to the output. But if it was a Moore machine, the output would be taken directly from the flip-flop where the output is 1. So this is a 1 hot. Notice that I have for every one flip-flop I'm using a for every flip-flop I'm using a corresponding to one state, and what I have is I want to make sure that either A is 1 all or 0, or B is 1 all or 0, C is 1 all or 0, D is 1. And this is called 1 hot. That means only one of the states is hot at the time. All right, then the problem is what if I start the circuit and the circuit resets, and the resetting brings my circuit into 0, 0, 0, 0. If that happens, that's not any of the valid states, okay? I only have 1, 2, 3, 4 valid states out of possibility of 16 possible states, because I have 4 flip-flops. There are 16 possibilities. Of these 16, I'm only using 4 valid ones. So the chance of me powering the circuit ending up in a bad state is pretty high. And therefore, what we do is we want to make sure that we have some kind of initialization. Okay, initialization. Let's initialize it so that when I power up, after I initialize, that powering up separate, the resetting is separate. Okay, but then after the resetting, I have an initialization signal that I want the initialization signal to start my circuit in 1, 0, 0, 0. Okay, so what do? I come into state A. So the color I'm using now, which is gonna be dark red, is for the initialization. Look, I'm gonna put an OR gate on the A input, but then I don't really need the OR gate because there is already an OR gate there. Okay, but just for the sake of consistency, let me put the OR gate anyway. Okay, and that OR gate, if I put a 1 on the init at the startup, okay, initialization, if I put a 1 there, I clock the circuit, there is a 1 that goes into A, but then I want to make sure that the rest of them become 0, and therefore I put AND gates for the rest. And then that same input complemented, that same input complemented goes to the inputs of the AND gates. Okay. So I'm going to clean this up. All right, let's look at flip-flop A. Okay. And I'm already seeing that I'm missing something. A with 1 has to go to B, which I have missed. So let's make that correction. A Okay. So A0 comes to the OR gate, and then another OR gate takes my initialization signal, and when the initialization signal is 1, that overwrites the blue OR gate and puts a 1 into the D input of A, and then clocking A becomes 1. Now that dark red signal gets complemented and goes to B, C, D using AND gates, and therefore when I put a 1 on the initialization signal, I'm putting zeros on the AND gate, and therefore the same clock that puts a 1 into A puts zeros into B, C, D, and therefore I initialize my circuit to 1, 0, 0, 0. All right. Remember the states where we had the encoding, we assigned 2 state variables, and we did everything with 2 flip-flops, and we ended up with no illegal states. But here we do get many illegal states. I will do another circuit here, and this one is much larger, far more number of states, so I'm not going to go into all the details I did with the previous one. I will just show you the diagram and some of the edges and some of the AND gates branching in, branching out, and so on. The circuit I'm designing is detecting 1, 0, 1, 1 simultaneous with 1, 1, 0, 1. Okay? Overlapping, meaning that if I receive a 1, 0, 1, 1, okay, I'm going to get a 1 over here. But then if I receive a 0, 1 after that, see, this is the first sequence, but then 1, 0, 1, 1, that's the second sequence. So I'm going to get another 1 over here on my output. And then again, if I receive a 1 here, okay, that is going to get my output to 1 because that is also a 1, 0, 1, 1. This is the first sequence. Okay, so this is sequence 1. This one is the first one, 1, 0, 1, 1, is again sequence 1. Okay, and then again you're seeing that this, let me change the color here, this one, 1, 1, 0, 1, 1, 1, 0, 1, that's sequence 2. Okay, what it means is it does consider overlapping sequences. And actually the one-hot implementation is really not that different from the previous one. What is different is the state machine that I'm going to be emphasizing on, and the state diagram that we start the circuit creation. This is the state diagram. So let's say that the way I'm going to do this is the following. I'm going to create a path, see, a path for 1, 0, 1, 1. Okay, I'm going to make that light green. Turned out to be yellow. Okay, I'm going to make a path for 1, 0, 1, 1, and then another path 1, 1, 0, 1. I fill the path, and then I come back and in the state diagram, and I come back and fill in the places that I only have one branch out. Okay, this is what I mean. I start in state A, and I do the second sequence 1101 here. 1 1 0 1 gets me to state A with a 1 output. And then I start in state A again. Okay. Now this path 1 0 1 1 1 0 1 1 takes me to state E, where my output is 1. Except the state B, I only have one edge out of each state. So let's fill them. Okay? And now I come in, I say if I'm in state A and I receive a 0, well, that's no good for neither one of those sequences, and therefore I remain in state A. Okay, so A has 2 edges out, which is enough because I have a J input. J can take 2 values, either 0 or 1. So each state has to have 2 edges out. B, I'm done with that. Okay, let's go to state C. I've received a 1, 0. If I receive a 1, I go forward. What if I receive a 0? I receive a 0, 1, 0, 0. Look at these two sequences. 1, 0, 0, or 2 zeros, no good for neither one of these two states, and therefore I go to state A. Okay? I'm done with A, B, C. Let's go to D. D. 1, 0, 1 has been received. If I receive a 1, I get happy, I go forward. What if I go to state D? I have received a 1, a 0, a 1, and then I receive another 0. It's not what I wanted, but this last 1, 0, is something that I can use towards a 1, 0, 1, 1 sequence. And therefore, takes me back to state C. Okay? Let's not do E. Let's go further down and do the state F. Okay? State F, I have received 1, 1 towards the good sequence or the second sequence, 1, 1, or H. If I receive a 0, I go forward. What if I receive another 1? Well, if I receive another 1, that's no problem because another 1 is giving me the input. Let me use blue. A 1, a 1, a 0. If I receive another 1, well, that is giving me still a 1, 1, and then maybe a 0. And therefore, a second one, a third one, a fourth one takes me back to state F. I'm done with F. Let's do G. G, I've received 1, 1, 0. A 1 gives me the second sequence complete. But if I receive a 0 in state G, again 2 zeros are no good for nobody, and therefore takes me back to state A where I start my search over again. All right, now I only have states H and state E. In the state E, let's go back to E now. In the state E, okay, I have to have 2 edges, a 0 and a 1. Okay, I've received 1, 0, 1, 1. If I'm in 1, 0, 1, 1, and I receive another 1, that can be, see, what you do is this. You look for the most number of bits that you can salvage, or you can use towards either one of those sequences. Here, the most I can do is just 1, 1. So let's go to the state where a 1, 1 has been saved, and therefore it goes into a 1, takes me to this state. If you are in E and you receive 1, 0, 1 1 you have already received, right? 1 0 1 1 you receive, and then you receive a 0. Okay, then again start looking from the right hand side, see what's the most number of bits that you can reuse, and therefore you only see a 1 0. It doesn't matter for which sequence it is. Okay, it is a 1 0, and then state I'm sorry, a 1 1 0, a 1 1 0, which is pretty good. Okay, and therefore a 0 in the state E takes you to a state where a 1 1 0 has been saved, which is state G. Okay, now let's look at the state H and look for the two edges out of state H. I am in state H. I have received 1 1 0 1. Another one, that's pretty good, because see, this is where I am here. I'm in state H. Okay, another one gives me 1 0 1 1. Well, incidentally, 1 0 1 is the next sequence, and therefore I go to this state where my output becomes 1. Actually, what happens from H to E, your output remains 1. Okay, what if I'm in H, 1 1 0 1 has been received, and I get a 0? Okay, what's the most number of bits that you can reuse from these? Only 2, these two last ones, and that is 1 0. That means you go to the state where 1 0 has been saved, which is this. Okay, what do I have? I have 1 2 3 4 5 6 7 8 states. If I want to do it the standard way, I have to have 3 state variables. For 3 state variables, I have 3 flip-flops. I need 3 flip-flops. I'm not going to do that. What I'm going to do is I will turn this into a 1 hot and use 8 flip-flops. True that I'm using far more flip-flops than the 3 flip-flops that if I do the 3-bit encoding. But then the logic on the sides of the flip-flops is going to be much smaller than if I were to do this using Carnot maps. Plus, I don't have to do Carnot maps. Okay, I go from this state diagram directly into circuit realization. What I'm going to do is I'm going to take a flip-flop with 2 AND gates here. Without getting there, I'm going to show you this. I'm going to take a flip-flop with set and reset. I'm going to put an OR gate on the side of it. I'm going to put 2 AND gates on the top of it, and then connect this to my J input, and then I'm going to repeat this 8 times. Okay, I'm going to repeat this 8 times. If this is, for example, representing C, okay, if this is representing C, state C, for example, okay, if this is representing state C, this goes to D, and if this is representing state C, this goes to A. And that's it. Okay? What you come up with is this circuit. Nicely, beautifully colored. Okay? And this is C. State C. 1 takes you to D. 0 takes you to A. Every flip-flop has an OR gate on the side of it. Some of them, like the H, B, and D. These 3 states there is only one edge going into them. Look down here. Look at B. There is only one thing going into B. Look at D. There is only one thing going into D. Look at, what was the last one? H. Only one edge, only from G goes into it, and therefore putting the OR gate there or not doesn't matter. Okay? And I don't need to go through the details of this because everything looks like the much smaller circuit. The state diagram obviously is different. The edges are different, but then the AND gates, the OR gates, they look the same. There are two differences here. One is the output. First of all, this is a Moore machine. And notice that in the I have two states where my output is 1E and H. Okay. Therefore, what's the output? If I'm in the state H, or if I'm in the state E, the output is 1. So what do? OR them together. Put an OR and take the one input from state H, one input from state E, and you're all done. The other issue that we dealt with in the previous one, we haven't shown it here, which I'm not going to do. That was the initialization, which we did with this dark red. For this one, I need to put it into an OR gate. There is already an OR gate, so let's keep it there. And then I complement this, put AND gates, put AND gates, put AND gates. Okay, I don't want to ruin the circuit, but then you put AND gates for 1, 2, 3, 4, 5, 6, 7. You see this. Okay, that's okay. There's a little room for putting the AND gates. And therefore my initialization initializes this to 1, 0, 0, 0, 0, 0. All right, so I'm done with the one hot implementation, and looks nice and easy to implement. Okay.